Hi everyone. In this video, we focus on the content-based addressing mechanism that's used in neural Turing machines. So basically, the idea is that you're fetching something from memory based on partial information about this thing, right? So you remember, it's like learning in humans, right? You remember a scene vaguely, or you remember a word vaguely, you remember some of the letters, and you want to fetch it. Now, when you go try to find that word in the memory or to find the content in the memory, it might be similar not just to one memory location, but to multiple memory locations. And the similarity could vary, right? So one essential component of the content-based addressing mechanism is a similarity metric that has to be defined between different content realizations, right? Or different contents for the memory cells. Also, typically, each memory cell will contain a vector, right? Rather than a scalar. And there are two reasons for that. Is that one, you want to offset the cost, so computational efficiency. So instead of, let's say I have a vector of 100 elements, instead of fetching each of the elements individually, let's say each memory cell has 10 elements, then I would have 10 read operations instead of 100 read operations. That's the first reason. The second reason, and actually like the core reason for the content-based addressing, is that it is enabled by having a vector in every memory cell, right? Because the more the size of the memory cell, the more the luxury that we have to have basically semantics inside each memory cell, right? So let's say I can store a single image in a memory cell. If I increase it to have a scene in a memory cell, let's say for video processing, then it could be even better in terms of the semantics, right? Because then I could define a similarity metric between scenes and I could recall a whole scene at once. That will both facilitate the computational efficiency, and it could even have statistical advantages or learning advantages, because it makes more sense, or the semantics are clearer or are interpreted directly, right? Instead of decomposing each scene into separate images. So one important thing is that with this addressing mechanism and with neural Turing machines that have access to explicit memory, now the problems associated with capturing long-term temporal correlations can actually be very different. So the traditional problems that we had with recurrent networks, like propagating information and gradients in the forward and back propagation, can be very difficult over long durations. Here, actually, that may not be a difficulty, because you can store these values in memory and then restore them after very long or after a large number of time steps, right? Now, there are variants of this implementation. In one variant, so as we discussed the neural Turing machines, the addressing is soft, meaning it's continuous, right? So I'm not going after only one memory cell, I'm going over a continuum, right? So there is a weight, right? So I'm going over multiple memory cells, and they are weighted by how much I want the output of the read operation to correlate or to be similar to the content of that memory cell, right? So an alternative mechanism that has better interpretation, but it could have more difficult optimization, is basically to view these coefficients as probabilities, which is what they are, and make discrete decisions, right? So go for the most likely one and then pick only one memory cell. If you are curious about this approach, you're welcome to read that paper called Reinforcement Learning Neural Turing Machines. Now, the optimization remains harder because it's easier with gradient-based learning to make decisions that are differentiable. Now, the last comment I want to say is that basically this neural Turing machine is identical or was developed in parallel for machine translation by what's called attention mechanisms. And if you're curious about this, you can read this paper, Neural Machine Translation by Jointly Learning to Align and Translate. Now, high level, why is it related to attention? Because not explicit memory not only enables content-based addressing and propagation of the gradient, but it enables having a very large network where you pay attention to only a small part of it while processing a certain input, whether in learning or in inference. Sounds good. This is a very open and I believe important research area, neural networks with explicit memory, just because it really happens in nature everywhere, and it seems that it might simplify a lot of the problems that are existing, but it has its own problems right now. It has very limited success in terms of applications. But hopefully when you do the project, you become curious about that field and contribute to it in the future. So that was the last video in the course. I hope these videos were useful and help you come up with exciting things in machine learning and deep learning in particular. Thank you very much.